Hi everybody, welcome in this masterclass on green hydrogen. We believe that green hydrogen will be the next revolution in the energy sector, and we are very enthusiastic about it because we believe green hydrogen is part of the journey towards decarbonization and a better world. Before we start, a brief word about EDP. EDP is today a global company present in 19 countries. We have 11.6 thousand employees, have an installed capacity of 27 gigawatts, produce yearly 72 terawatt hours. We have 11.6 million clients, and we are the fourth worldwide operator of wind energy. We are not the biggest utility, but we do believe we are the right size. We are big enough to go after any opportunity which we consider worthwhile, and we are small enough to move fast and to relate to startups as we have here at the WebSummit. We have in our DNA both renewables and innovation, and we are very pleased to be able to present here at WebSummit. We want to lead the energy transition, and for that our vision for 2030 is decarbonization, digitalization and decentralization. And for that we aim at having 90% renewable generation, reduce by 90% CO2 specific emissions, become coal-free, have more than 4 million decentralized solar panels installed, more than 1 million clients with e-mobility solutions, and 100% smart grids. Now speaking about hydrogen, hydrogen is a very special element and an excellent tool for the energy transition. It is the first element of the periodic table. It is the most common element in the universe. It does not exist isolated in nature. Two atoms of hydrogen make one molecule of hydrogen. Two atoms of hydrogen plus one atom of oxygen makes water. Four atoms of hydrogen plus one atom of carbon make methane. Hydrogen is part of most fossil fuels, and most important, it burns at high temperatures, producing only heat and water. The name hydrogen comes from the Greek and means maker of water. It is interesting to place the hydrogen in the hype curve, and we see that around 2002 there was a peak of inflated expectations. By that time, Jeremy Rifkin wrote a book called The Hydrogen Economy, and he made conferences on the subject all over the world. He was a couple of times here in Portugal, and I attended to one of his conferences. Looking back, he was mostly right. However, the technology was not yet there. Namely, renewable energy had not yet reached the present development and present low costs. Then followed the trough of disillusionment, and today, by 2020, we are at the slope of enlightenment. How did we reach this point? Because when hydrogen was on the trough of disillusionment, many people did not give up. At academia, at the industry, many clever people went on studying the subject and making developments and leaping forward, betting a lot that hydrogen would be important to humanity and very good business. We have here to point out Japan, which never gave up building a hydrogen society. We believe then by 2030 hydrogen will reach a plateau of productivity. Since Edison, there is a war going on between molecules and electrons. I myself, working at EDP, have always been on the side of electrons. But I have to accept, when it comes to hydrogen, electrons and molecules are not competitors. They are part of the same electrification system. They are complementary. Why are they complementary? Because hydrogen is fundamental to tackle hard to electrify sectors. Take aviation, shipping, glass and cement, high temperature iron and steel furnaces, agriculture, chemicals, pulp and paper, food processing, and you need hydrogen. Most of all, you need hydrogen as feedstock for many chemical industries. More than 80 million tons per year of grey hydrogen are produced just to be used as feedstock. It is important now to point out that there are three types of hydrogen: the grey hydrogen, the blue hydrogen, and the green hydrogen. The grey hydrogen is the one which is mostly used today. It corresponds to 99% of the uses, and it is made from fossil fuels and generates a huge amount of CO2. Blue hydrogen is basically grey hydrogen to which we add the sequestration of CO2, namely in caves. And green hydrogen, which is the one which we care about, is produced from renewable energy with water, producing hydrogen and oxygen, and we'll be speaking more about it. Hydrogen is produced from water with electricity with two types of electrolyzers: the alkaline electrolyzers and the PEM electrolyzers. The alkaline electrolyzer has been around for some 100 years. It is quite mature. It has still to scale up to reach present demand. The PEM electrolyzer is the one on which many people is betting these days and brings in the promise of more efficiency and less cost. Both differ primarily just on the ionic charge carrier, as well as in the actual electrolytes used. First, before we proceed, some back of the envelope figures. If we take 55 kilowatt-hours of electricity, 9 liters of water, feed them into electrolyzer, and we get 1 kilogram of hydrogen and 8 kilograms of oxygen. Another example, this one on mobility. If we take 302.5 kilowatt-hours of green electricity, add to it 10 buckets of water, 50 liters, around 50 liters, feed them into electrolyzer, we make 5.5 kilograms of green hydrogen, and that takes a fuel cell electrical vehicle 500 kilometers. Isn't that amazing? Let's recap. First, green hydrogen can be made from renewable energy by using electrolyzers. Second, hydrogen has high energy density. 1 kilogram has 33.6 kilowatt-hours, which compares quite favorable with diesel, with just 13 kilowatt-hours per kilogram, and much more with the battery of lithium-ion, with just 0.2 kilowatt-hours per kilogram. But bear in mind that hydrogen has very low specific mass at normal conditions. 1 liter of hydrogen is just 0.09 grams. It means that to have 1 kilogram of hydrogen at normal conditions, I need 11,000 liters. And this does put a challenge, because to be of any practical use, we'll have to compress the hydrogen. Typically, we compress the hydrogen at 350 atmospheres or 700 atmospheres. That is what is used in mobility. Cars use 700 atmospheres to save space. Coaches and buses and trucks, they typically use 350 atmospheres. And then we can put 1 kilogram of hydrogen in 16 liters or 32 liters at 350 atmospheres. Other than being compressed, we have another solution, is to liquefy the hydrogen. Now here again we have a challenge, because to liquefy the hydrogen we have to cool it to below minus 253 Celsius. That is just 20 Celsius above the absolute minimum. And this operation consumes more than 30% of the energy content of the hydrogen. However, if we want to carry the hydrogen very far away in a truck or in a ship, this may well be the best solution. I would like also to point out that hydrogen can be transformed into other carriers for storage and transport. Typical ones are ammonia, which is NH3, or methane, which is CH4. The processes have been around for years. To make ammonia you use the Haber-Bosch process. Typically to make methane you use a fixed bed Sabatier reactor. And again, other than being a carrier, both ammonia and methane are also products which can be used as feedstocks for many industries. We have been speaking about different carriers. Hydrogen, like electricity, is not a source of energy, is a vehicle or carrier of energy. And here I would like to point out that the efficiencies measured from the generation to the wheels, which is normally called well-to-wheels efficiency, are quite different. Electricity is the winner, and so we may conclude that whenever possible, go for electricity is the best carrier, because it has a well-to-wheels efficiency of 73%. Hydrogen has just 22%, and if we are using synthetic fuels, we would have just 13%. Here I have a diagram by Toyota, which shows that there is room for the different types of fuels. And vocation of hydrogen is situations of large vehicle sizes and long driving distances, the so-called long-haul transportation. That means a truck which on one day runs 1200 kilometers, refuels, changes driver, and does another 1200 kilometers. That is the vocation of hydrogen, very difficult to achieve with electrification, because just notice a long-haul transportation truck with 40 tons, which would have the capability of doing 750 kilometers, would have to have a battery of 1 megawatt hour, which by itself would weigh 6 tons. We may now wonder what will be the future of sustainable mobility. Will it be hydrogens? Will it be batteries? Again, they can be allies. Here I am comparing the Toyota Mirai with the Tesla Model S, and although I would prefer any day the Tesla, I have to accept that the Mirai has its advantages. It refuels in just 3 to 5 minutes. The storage system weighs just 195 kilograms, which compares to 570 kilograms. And if I wanted to double the range, the full weight of the storage system would just be 288 kilograms, and that would compare with 1140 for the Tesla. Then why would I prefer the Tesla? Because electricity is much cheaper than hydrogen. I would run the Tesla much more economically than the Toyota, but above all, there are many more charging stations for an electrical vehicle than refuel stations for hydrogen for a fuel cell electrical vehicle. Therefore, I definitely, presently, I would prefer an electrical vehicle. As I mentioned before, Japan has been betting on hydrogen for years, and realizing that they do not have too much renewable energy, they came with a clever idea of importing hydrogen from countries where there is a lot of space and there are good resources of renewable energy. And so they launched a pilot called ISTRA between Australia and Japan, where the hydrogen is produced in Australia and shipped on a special vessel to Japan. It is shipped in the liquefied form. I think this is a very clever idea because it raises the concept of exporting renewable energy. It could be considered that in summer, when the resources are huge in the northern hemisphere, renewable energy would be exported to the southern hemisphere in the form of hydrogen, and in winter hydrogen would be shipped from the southern hemisphere into the northern hemisphere. In Europe, the Netherlands are having a similar vision. Rotterdam is positioning itself as the energy port of northwest Europe, and for that purpose it's considering importing hydrogen from different places in the world, namely from Portugal. What are we doing with hydrogen at EDP? We consider hydrogen the electrification ally. The rationale behind it is an important piece in the decarbonization puzzle, complementary to electrification to address hard-to-abate sectors. It empowers renewables, and those renewables intermittency and stabilizes renewables revenue. It provides storage and flexibility, can serve as an energy buffer and a strategic energy reserve. Our action plan is presently the following. We are developing a power to hydrogen pilot project NCCGT, and there we are testing the power to H2 to power concept, which will help enhance the CCGT flexibility. We are doing an offshore hydrogen wind coupling project, with which we intend to study a solution to produce hydrogen from offshore wind at wind parks. Then we are also testing or starting pilots of hydrogen and uses referring to mobility, trying to develop a national market there. And fourth, in alliance with the Netherlands, we are developing a project which is called H2 Sines with other Portuguese partners, where we have the vision of by 2030, if all goes well, having installed a 1 gigawatt of electrolyzers. Half of the hydrogen produced there will be exported to the Netherlands. The other half will be used locally on the industry, on the petrochemical industry which exists there, will be blended into the natural gas pipeline and will be sent by road to hydrogen refueling stations to be used in mobility throughout the country. Now, an important question: will this have a business plan? Will it be economical? We believe yes. Presently, grey hydrogen costs just 1.5 euros per kilogram. whereas green hydrogen would cost around 4 euros per kilogram. But green hydrogen will have a price which will tend to increase because it will have to be progressively decarbonizing, becoming blue hydrogen, whereas green hydrogen will tend to decrease with the evolution of the technology. And it is important to realize that the price of the green hydrogen has to do with the cost of the electrolyzers and the cost of the electricity, 31% being due to the capex and 45% to the price of the green electricity. We believe that both these values will tend to decrease. The electrolyzers cost will decrease by 50% until 2030, and the electricity will decrease at least by 10–20%. To conclude, hydrogen is a story we must write together. It is a huge bet by the EU towards decarbonization goals. There will be several and good opportunities for startups. Together, we will build a better planet. Thank you.